Students, today in this session let us discuss another property of analytic function, which is an orthogonal property. So what is orthogonal property and what is the statement, and is there any results to be proved, or these are the content that we are going to discuss here now. So what is orthogonal property is? The statement of an orthogonal property is that if f of z is equal to u plus iv is analytic, then the family of curves u of x comma y is equal to c1 and v of x comma y is equal to c2. C1 and C2 being the constants intersect each other orthogonally. So if f of z is equal to u plus iv is an analytic function and u and v are the functions of x and y which are being taken as family of curves, and these family of curves intersect orthogonally is the statement of orthogonal property. The angle between both the curves must be 90 degrees. So let us prove the result. We know that two curves intersect each other orthogonally if the tangent at the point of intersection are at right angle. So when do we say two curves intersect orthogonally? Whatever we do with respect to the curve, it is mainly with respect to the tangent drawn to the curves. So we have considered u and v as the family of curves, and there is a tangent drawn to both the curves, and the tangents of both the curves intersect orthogonally. The angle between those two tangents must be 90 degrees. So we know that dy by dx represents the slope of the tangent. So by the definition, dy by dx is a derivative, and geometrically it represents the slope of the tangent. And the condition for perpendicularity of two lines is that the product of their slopes must be equal to -1. So there are two cases where we say they are orthogonal, the curves are orthogonal. One is with respect to the angle, the other one with respect to the slope. So if slopes of the tangents drawn, if the angle between them, if the slopes, when we multiply the slopes, product of the slopes results in -1 is the one case, and one way of proving the curves are orthogonal. The other way is that angle between the tangents is 90 degrees. So two ways we can prove that the curves are orthogonal. So here both the ways I had specified, and let us see which is going to be suitable for us to use to show that the curves are orthogonal. So consider your real part of the f of z analytic function, that is u, which is equal to c1, and differentiating with respect to x, treating y as a function of x. So here u is a function of x and y, and differentiation has been done with respect to x, and treat y as function of x here. So when we do that, the differentiation of u of x comma y is equal to c1 gives us dou u by dou x plus dou u by dou y into dy by dx, which is equal to 0. So here dy by dx is the slope, which is nothing but dou u by dou x divided by minus dou u by dou y. Sorry. So from this equation, we can get that as dy by dx is equal to dy by dx is equal to, we can write it as minus dou u by dou x divided by dou u by dou y. Dou u by dou y. So dou u by dou x can be taken as ux, and dou u by dou y is uy. So let this be is equal to m1, that is first slope. Similarly, consider the other curve, other family of curve, which is v of x comma y is equal to c2, and differentiate that with respect to x. So when we do that, we get this equation, that is our second slope. So now let us consider the product of the slopes. Consider m1 and m2 in product, m1 into m2, and substitute for m1 and m2, and simplifying we get this. And since f of z is analytic, we have CR equations which satisfies the function ux is equal to vy and vx is equal to minus uy. So use these in the above step. So use this condition in this above steps. We get m1 into m2 is equal to vy into vx has been replaced by minus uy, and uy is there as it is, and vy is also as it is, which is equal to -1. So when we simplify, we get the answer as -1. Hence the curves intersect orthogonally at every point of intersection. So this is the proof of orthogonal property of a function f of z with the family of curves u of xy is equal to c1 and v of xy is equal to c2. And whatever we have proved till now was it in the Cartesian form. So the same result, let us see in polar form also how was that satisfies. So the statement is if r is equal to f of theta, we know that tan phi is equal to r d theta by dr, and phi being the angle between the radius vector and the tangent. The angle between the tangents at the point of intersection of the curves is phi 1 minus phi 2, and tan phi 1 into tan phi 2 is the condition for orthogonality. Tan phi 1 and tan phi 2, here it is missing, so tan phi 1 and tan phi 2 must be equal to minus 1. So remember this, it has not been seen here, this minus 1, and this is a condition for orthogonality. So now let us try to prove that result. Consider the first family of curve, that is u of r comma theta is equal to c1, and differentiate with respect to theta, treating r as a function of theta here. So once we do that, we get dou u by dou r into dr by d theta plus u theta is equal to 0. And from this we can get it as dr by d theta is equal to minus u theta by ur. So let this dr by d theta is nothing but the slope, which we can take it as tan phi 1. Tan phi 1 is equal to r d theta by dr. We can take r d theta by dr, and which can be written as r into ur by u theta. So now similarly, let us consider the second family of curve, that is v of r comma theta, and differentiate that with respect to theta and treating r as a function of theta, and doing all this procedure again, we will end up with tan phi 2, which is equal to minus r vr by v theta. So this is our second slope. Now consider product of the slope. So product of the slope is tan phi 1 into tan phi 2, and if the product of the slope is minus 1, then we can say the family of curves are orthogonal. So in order to prove that, let us substitute for tan phi 1 and tan phi 2. So once we substitute it and use the CR equations, so CR equation in polar form are given by r ur is equal to v theta and r vr is equal to minus u theta. That is CR equations in polar form. Let us use this CR equations in this formula. So we get it as tan phi 1 into tan phi 2 is equal to minus 1. So r into ur is there as it is, and u theta can be replaced by minus r into vr in the denominator, and this v theta can be replaced by r into ur. So everything gets cancelled here and we get the answer as minus 1. Hence the polar family of curves u of r comma theta is equal to c1 and v of r comma theta is equal to c2 intersect each other orthogonally. So this is the proof of orthogonal property in polar form also. So what we have seen in this session is proving the orthogonal property for a function f of z which is equal to u and v, u plus iv, where u is equal to c1 and v is equal to c2 have been taken as family of curves, and these family of curves intersect orthogonally. The result has been proved both in Cartesian form as well as in polar form. So this is about the session. Thank you.